Okay, today we'll model an overhead water tank, a rectangular one, with these dimensions. So we'll have dimensions like this. So we'll assume that it is supported by a frame structure, reinforced concrete. Okay, we'll assume this distance as 3 meters, 3 meters, 3 meters, and 3 meters. So the bay width in x direction is also 3 meters, and similarly in the y direction. The water tank alone, it has 6 meters into 3 meters. And for the modeling purpose, we'll not consider a freeboard, which is the distance kept free from the top of its water tank. So yeah. Okay. And all things good. So we can model the tank now and go over to the SAP. So I have chosen new model and make sure the units are consistent. So I have been working with kilonewtons, meters, and Celsius. So I'll keep it as same. And since this is a frame structure, I would go with this 3D frame, right? So number of stories, we have 4 stories. Base in x direction is 2, y direction also 2, story height is 3, width is 3 meters. This is also 3. So this is number of bays and the bay width, right? So now we have this. There are several categories for your reference you can have a look at. And if you need, you can define the beams and columns here also. That's also an option. So, and if you want to customize your grid, so the grid I have chosen is having regular intervals, whereas if you have a different intervals at several locations, so you can do it. So for now, I have the reference and I'll click OK. So now I have the grid and as well as the frame structure also, right? So yeah. Okay. So I'll go ahead and define the materials first. Make sure your units are here, kilonewtons meters Celsius you are working with. So one thing I forgot, like if you want to edit your grid data, so go to, right click on this menu, so sorry, the window, and you have edit grid data and modify, and you can select whatever the grid you want to change, X, Y, or Z. Make it as spacing, so you'll have 3 3. So if you want to change the third Z into 4, if your tank height is 4 meters, you can change it from here. And for the moment I will click OK, and now changes done. So now I need to draw my tank here, right? So I'll use, first I will define the materials. Materials I have, so 40,000, sorry, 4,000 psi is usually the concrete material. So I copy the material and grade 30. Grade 30 concrete. Right, 24. Grade 30 usually have 27. Poisson ratio is 1.5. All done. Yes, you don't need to change others much. Okay, that's done. So we'll use the same grid. If you have different grids, usually for water retaining structures, large structures, we use 35 grade A concrete, which is aqueous concrete, right? So that can also be done by defining different grades of concrete here. And the frame materials, frame sections for the columns and beams, I will use the same. Add a copy of the property frame, where I will use 0.3 by 0.3, which is a fairly large section. Go with 0.25 by 25. Okay. So it is an I section. It's not an I section, sorry. You have to add new property. Concrete, rectangular. It is noteworthy that I did not do any preliminary calculations. So these are my rough estimation for the initial sizes. So if it is not satisfactory, definitely you have to increase it. All done. Right. So I'll select all and assign. Once you define the material and the section, go ahead and assign it. And this is the frame section. So now it's done. So in this part, you have the tank actually. So okay. So now I can go ahead and draw the tank. So I use this draw poly area, right? it's done. Press enter. 2. Press enter. Okay, the sides have been drawn, so I will draw the bottom slab also. So this is the bottom slab. So if you want to fill these elements and go to display, not display options. Okay, set display options, and general view type is fill objects, and you'll see the tank, right? So once the tank is drawn, you no longer need these this frame and these columns. These 5 and these columns you don't need because it's a rigid wall. Make sure that you don't select necessary parts. So we need the beams at the bottom level of the tank. What we don't need is these 1, 2, 3, 4, 5, 6, 7, 8 9 columns and the beams on the top. So we can press delete. All things done. Right. So now we have approximated in this mathematical model, the tank is supported by a frame structure, and the frame structure is being supported at the ground. So I will now mesh these areas. So each is 3 by 3. So I need to at least go with so I will first go with 3 by 3 mesh. Divide the area, each area by, so you will notice that each area is 3 into 3 meters. So I will divide it by 3 into 3. So each area will be divided into 9 squares. right? And each small square is one uh, 1 meter squared, right? This might not be uh, a good mesh, so we will first play with the values and see what will happen, right? Now I will go and define the slab material. So this frame, not the frame section. So I'll go with area sections. It's a type of shell. Add a copy of the shell. So this is the water tank. So I will have a point, let's say 0.15, right? Water tank sides 0.15. So shell thin and click OK. And for the bottom, bottom slab, I will make it as zero point 0.2. The same material, it's done. So once you define, you have to assign it. So in this way, you can select all the sides. So look at how I did it. It's not the weaving option. So if you choose it like this, only this. So you are now in a 2D plane. Only your 2D plane will get selected, right? Usually, if you need to do it, make sure you are in a 3D view. So you can rotate it in a way that when you select it, your bottom slab will not get um, selected, right? So I have told this in earlier tutorials as well. So if you choose from left to right, whatever the parts in the inside this blue color box will get selected. But if you go from, sorry, if you go from left to right, so only the full elements will get selected. If you go from right to left, whatever the things in the box will get selected, right? So you can do it. Another way to do is let's say you are in 2D view, so you can go to view and set 3D view and plane is XZ, set the aperture to 0 and press OK. So now, even though if you are in 2D view, all the things will get selected, right? So you can assign area section. Oops, haven't I defined? Oh, water tank side. Okay. Water tank bottom. It's okay. This is the side. Okay. So once you select this, your slab will get, bottom slab will get selected. Assign area sections. That's done. So all things are done now, right? So I'm not happy with the mesh, so I will go ahead and don't worry if your frame sections are get selected, since we are applying on only to these areas, those will only get meshed, right? So divided 2 into 2 by each square, right? Now we are working with each small square, right? So they will be divided into, so it's now fairly good, right? So, right. Now I can go ahead and first I need to, so now you have water pressure in this tank. So from the top of the tank, right? So if I draw it, it will look like this, right? So the tank is like this, right? So filled with water to the top level. So water pressure is usually on this wall, and each wall it is triangular, right? So it's 0 at the top and certain value at the bottom. It's triangular, right? But you'll notice that the bottom slab, that pressure is uniform, right? This pressure, let's say this is X, the pressure. So this X pressure will be acting uniformly to the bottom slab, right? You know the basics of water pressure, right? At each, so it is always, pressure is always perpendicular to the surface, right? No matter what the planes they are acting on, right? So first we have to find this pressure, right? So we have now a simple calculation for this pressure. We apply it by a joint pattern, right? So first we'll clear this. You can check my ETABS videos. I have clearly explained how this triangular variation is coming, right? And there I have modeled a simple cylindrical water tank which rests on on a floor, right? So you will see, so this is the Z equals to 9 and this is Z equals 12, right? So SAP usually assign the pressure by a joint pattern. So if they have something called like this AX BY CZ plus D, right? So what you and me know is the triangular variation, right? For this triangular variation at Z equals 12, we know uh, the pressure is 0, right? Right. So we don't usually deal with these two since we are working in a linear way, right? The pressure distribution on Z axis, right? So they will not be coming. We are checking this triangular distribution along Z axis, right? So we'll only remain with these two parameters, and we have CZ plus D. So we don't know the value of C, but this is 12, Z is 12, and D we don't know, right? And we'll remain with D is minus 12C, right? And similarly, at Z equals 9, right? Uh, the water pressure is, we can see it is 3 meters, right? Is that right? 3 meters means H rho G, it's 3 into 10, right? So this is rho G, right? I think it is in kilonewtons per meter cube, right? So we usually take rho G as 1 unit and multiply the H value, right? I think better to check it. I think this is in kilonewtons per meter cube. So once you multiply it by a meter unit, so always make sure the units are consistent with your system that you are modeling, right? So you know what you're modeling, right? And this is 3 meters, so that's okay, right? And this is C into 9 plus D, right? So this will be 30 is equal to 9C plus D is 12C minus 12C, right? So you will remain C is what? C is minus 10 and D is 120. So your pressure variation is given by minus 10 into Z. It's your joint pattern. One thing you can, so you have to make sure that your Z is not starting from here, right? So you are in the global axis system. So your Z starts from here, right? Z is 0. Don't ever calculate Z is from here and solve these equations. Then you'll go wrong, right? So you have to make sure that point. And other than that, it's a simple calculation. So now you will see C is minus 10 and D is 120. So you will go with these parameters to set 2000. And first, yes, I have to define my load patterns, and did I have right? Yeah, self-head multiply is done. I will not apply any live load for now. So the water pressure also you can apply as a dead load, right? So first you have to define a joint pattern, new joint pattern, water pressure at new joint pattern, okay. And then, so the joint pattern should be applied to these balls, right? These side balls. The joint pattern you have to define water pressure. This is constants, you will remember that it's minus 10 and this is 120, right? So always keep this. So if you accidentally add the same value, so the ones you have assigned earlier will be deleted. So that's better, right? So it's done. So you will see the values here, right? So I did not see the direction still. So we'll go with area load, surface pressure. Yes, you will see it is automatically there, right? So that load. So this top and bottom means which side of the area element. So you can go with the local axis of the area elements, right? And the blue color axis usually go if it is going uh, out from the surface, so that will be taken as one. So let me show you. I think it is. So make sure this is replace existing. So I didn't see that arrow, so that's why I'm replace adding it again. So I will replace the same thing. So this can be either one or negative one based on the direction I have shown you, right? So let's see. So you will see, right? If it is bottom, right? So you will see the pressure is acting from inside inner side of the tank to the outside. So that's what you which should happen, right? So if it is in the other way around, you have to multiply it by a negative value, right? And for the bottom slab, oops, we'll select this. At the bottom, the pressure is we have calculated, right? 30, right? Yeah, the pressure is 30, so you can assign area loads surface pressure by element. It's 30. So now you don't need any joint pattern since it's a uniform pressure. So we have to see in which direction. Loaded phase will keep top and see. So I think it is wrong because the pressure should be applied on the negative is a direction, right? So in that case, this should be seen as negative 30. So I think we have applied in the wrong direction. So we can select all these things again and apply the area load. This is negative 30. Or else you can, right? So this, the element. So make sure you are replacing the earlier load. Now it's done, I think. Yes, it's done. So your tank is now ready. So you can go ahead and run the analysis. For the moment, I will not run the model analysis. So right now we have to save it. The tank. Right. So you have the results here if you want to check bending moments, so M1 and M22. So I have done several tutorial how to read this output from the SAP 2000 M1 on M22. What are these things? So I have given a detailed explanation on these values in a separate video. I will put this in the description, link in the description, how to read these uh, values, because you don't know what are these, right? F1 on F22, they're in a certain uh, coordinate system, right? With respect to their local coordinate system, and the stresses also, right? So S max max, SVM, and you have to know these things if you are using this software, because modeling and getting some results is easy, but as an engineer you have to interpret it. In order to interpret, you have to know which what does these what does this value mean, right? So if you go to the displacements, you will see, so it is displacing each. Also this point, it is a 1 millimeter, right? 1 millimeter, and the bottom slab, so it is, yeah, nearly 1.6 millimeters, right? The displacement, so fairly small. That's okay. So we'll check the frame. So that's quite okay. You will see. Uh, so we have used fairly large section. You will see that the displacement is less than 1 millimeter, right? So, and if you need to see the bending moments, the axial forces, you can see, right? And then, sorry, the bending moment, the values you can see. So if you right click on the element you need, so it will give you the value, displacement, and the shear force for the dead load case, right? So one thing you can do to verify these is, now you know the load of water you have, right, from this pressure, and you calculated the water volume is 6 by 6 into 3, and based on the concrete volume, the walls and frames, you can calculate the total load which is transferred to the columns, and you can sum these reactions at the supports, for example joints. You can sum these values in the Z direction and see whether the value is the value is okay with the manual calculation, right? If not, there should be something off, right? You have to check your model, right? That validation is very important, since the software can give any value based on your inputs. If your model is correct, the values you choose from the model in order to do the design are also correct, right? So you can play with these values. So for example, if you need, you can change these, you can do a finer mesh. It, yes. So I will divide it by 2 by 2 again. I'm not sure whether it will run because my computational power is not that good. Maybe it will run. It is not that bigger mesh, right? Yeah, that's done. And if you want, you can even change the sizes and see. Let's say we'll change these into 100. Okay. And see what will happen. This is also 100. It's also 100. So we'll run this one and see what will happen. You can check the bending moments in either direction. And then the displacements. So this is the displacement contour, the resultant displacement. So you will see still we are getting something around 2 millimeters, right? But check this out in the x direction, or I'm not sure it is x or y. So U2 in the horizontal direction, it has 7 millimeters. So that means your section is not that thick, right? So 7 millimeters is almost close to 3. Not, no, sorry. So 7 millimeters, right? So closer to 1 centimeter, right? That's okay. And here, yes, the same thing, right? So that's done. So I hope you got the idea. So the concept is how you, so the most important thing is how you approximate this, how you approximate your real world structure into a mathematical model in SAP 2000, right? And the things you are doing, you have to verify. Things you apply to the model, you should know why and what are the outputs I can obtain from this, right? So, so that joint pattern is fairly simple thing, but it is a concept that we idealize the water pressure, right? It is how we idealize the water pressure on this each wall. And the bottom wall, you know that the surface pressure is uniform. So apply it as a uniform pressure, right? So if you need to see the local axis, so you can go ahead with this, and areas show local axis and press OK. Does it show? No, right? You have to unlock it. Yeah, now it shows, right? So what I mean with these local axis is clearly described in that video I have provided in the description. So if you want, you can check that. Yeah, that gives a detailed explanation on how you model and more importantly, what you interpret, right? Okay, hope you guys enjoyed. Okay, thank you very much.